Kita bossa science, kwano kwa beti science, rafu ya bossa science, truth na beta, truth na omega, truth na alpha science.
The Science Foundation College enamave ku Lwejjinja ng'oyingira kilomita emu. Ssomero lya Dene Boarding ery'abawala n'abalenzi. Ku O-level tusomesa arts ne sciences ate A-level tusomesa sciences zokka. Omwana mulete ku The Science Foundation College. Ffe tusinga okusomesa sciences. Okumanya ebisingawo kuba ku 0753 8 27 09. The Science Foundation College, based on sciences and based for sciences.
Dr. Bossa is a teacher at the Science Foundation College, the best school that teaches sciences. At A-level, we teach sciences only. At O-level, we teach arts and sciences. Today, 10th of May 2019, we are going to consider solubility of sparingly soluble salts in water. For instance, when sparingly soluble salt like lead chloride is dissolved in water, a little dissolves to form ions in the solution, and an equilibrium is established between ions and solution. Lead chloride dissolved in water to form lead ions plus 2 chloride ions. Then an equilibrium is established between the solid and the ions. The solubility constant Kp is given by concentration of lead ions into concentration of chloride ions. Then the implication of Kp, the higher the Ksp, the more soluble the salt. So you can even compare the solubility of salts from their Ksp. The bigger the Ksp, the more soluble the salt. Application of Ksp to calculate the solubility of salts in water. Example 1. The solubility of silver chloride at 18 degrees Celsius is 1.46 times 10 to the power negative 3 grams per decimeter cubed. Calculate the solubility product. Remember that when you are calculating solubility product, the concentration of ions are expressed in moles per decimeter cubed. First, find the RFM of silver chloride, which is equal to 108 plus 35.5, which is equal to 143.5 grams. Then we get the molarity. Molarity is equal to concentration grams per liter over RF M. Molarity is equal to the concentration in grams per liter, which is 1.46 times 10 to the power negative 3 over the RFM, which is 143.5, and this is equal to 1.0 times 10 to the power negative 5 moles per decimeter cubed. When you write an equation of silver chloride, it will give you silver ions plus chloride ions. It means that 1 mole give 1 mole and 1 mole. Therefore, 1.0 times 10 to the power negative 5 will give you 1.0 times 10 to the power negative 5 moles per decimeter of silver ions plus 1.0 times 10 to the power negative 5 moles per decimeter chloride ions. Case P will be equal to concentration of silver ions times the concentration of chloride ions in moles per decimeter, which is equal to 1.0 times 10 to the power negative 5 times 1.0 times 10 to the power negative 5, which is equal to 1.0 times 10 to the power negative 10. But this is moles per decimeter times moles per decimeter, which is moles squared per decimeter to the power negative. Example 2. The solubility of calcium hydroxide in water at 20 degrees is 2.78 grams per decimeter cubed. What is the solubility product? Remember, when calculating the solubility, the concentration of ions is expressed in moles per decimeter cubed. So we are going to first find the molarity of the solution and then calculate case P. To determine the molarity of the solution, we first get the relative formula mass of calcium hydroxide. Calcium hydroxide is equal to 40 plus 2 into 16 plus 1, which is equal to 74. Then molarity of calcium hydroxide is equal to concentration grams per liter over RFM. Then molarity is equal to 2.78 grams per decimeter over 74, which is equal to 0.0376 moles per decimeter cubed. Then when you write the equation for ionization of calcium hydroxide, it gives you calcium 2 plus aqueous plus 2 OH ions. 1 mole will give you 1 mole and 2 moles. 0.0376 moles per decimeter of calcium hydroxide will give you 0.0376 moles per decimeter cubed of calcium ions plus twice these moles of hydroxide ions, which is equal to 0.0752 moles per decimeter cubed. Then case P is equal to concentration of calcium ions into concentration of hydroxide ions squared, and this will be equal to 0.0376 times 0.0752 squared, which is equal to 2.13 times 10 to the power negative 4 moles per decimeter. Example 3, calculate the solubility of barium sulfate in 1 water, 2 0.1 molar sodium sulfate solution, 2 0.2 molar barium chloride solution. Case P is equal to 10 to the power negative 10. First we write the equation. Barium sulfate dissolves in water to give barium ions, aqueous, plus sulfate ions, aqueous. 1. If X moles ionize, you get X moles, you get X moles. Case P is equal to concentration of barium 2 ions into concentration of sulfate ions, and this becomes 1 times 1 to the power negative 10 will be equal to X times X squared is equal to 10 to the power negative 10. X is equal to 10 to the power negative 5. Therefore, solubility of barium sulfate in water is equal to 10 to the power negative 5 moles per decimeter cubed. 2. Calculate the solubility of barium sulfate in 0.1 molar sodium sulfate. Supposing X moles dissolve, X moles of barium ions will be formed, plus X moles of sulfate ions will be formed. Also, sodium sulfate will ionize to form 2 sodium ions plus sulfate ion. So 0.1 mole will give you 0.2 moles of sodium ions and 0.1 mole of sulfate ions. In the solution, the concentration of barium ions will be equal to X. The concentration of sulfate ions will be equal to X from sulfate, from barium sulfate, and then 0.1 from sodium sulfate plus 0.1. But X is very small, that X plus 0.1 is approximately equal to 0.1. Case P, which is 1 times 10 to the power negative 10, will be equal to the concentration of barium, which is equal to X times the concentration of the sulfate, which is equal to 0.1. Therefore, X is equal to 10 to the power negative 9. Therefore, the solubility of barium sulfate in 0.1 molar sodium sulfate is equal to 10 to the power negative 9 moles per decimeter cubed. Part 3. Calculate the solubility of barium sulfate in 0.2 molar barium chloride. Case P is 1 times 10 to the power negative 10. Here also barium sulfate ionizes to form barium ions plus sulfate ions. If Y moles dissolve, it will form Y moles to form Y moles of the sulfate. But also the barium chloride will dissolve to give barium ions plus 2 chloride ions. But 1 mole will give 1 mole, so 0.2 will give 0.2 and 0.4 moles per decimeter of chloride ions. Then in the solution we shall have barium ions equal to Y plus 0 0.2 moles from barium chloride. But Y is very small, so this is approximately equal to 0.2. Then the concentration of the sulfate ion is in the solution will be equal to Y. From case P, which is 1 times 10 to the power negative 10, will be equal to 0.2 times Y. Y is equal to 5 times 10 to the power negative 10. The solubility is 10 to the power negative 10 moles per decimeter cubed. We found that the solubility of barium sulfate in water was 1 times 10 to the power negative 5 moles per decimeter cubed. We have also found that the solubility of barium sulfate in 0.1 molar sodium sulfate was 1 times 10 to the power negative 9 moles per decimeter cubed. We also found that the solubility of barium sulfate in 0.2 molar barium chloride was 5 times 10 to the power negative 10 moles per decimeter cubed. We see that barium sulfate is more soluble in water than in the solution which contains sulfate ion or in the solution that contains barium ion. This brings us to common ion effect. Common ion effect is the reduction in the solubility of aspiring the soluble solids in a solution that contains a common ion. In the previous example, we saw that barium sulfate was more soluble in water than a solution that contains sulfate ions or barium ions. Example 4, explain how the solubility of silver chloride in water will be affected by addition of the following substances. A. Sodium chloride. The solubility of silver chloride decreases when sodium chloride solution is added due to common ion effect. A. Sodium chloride solution. The solubility of silver chloride decreases when sodium chloride solution is added due to common ion effect. B. Ammonia. Solubility increases due to formation of a soluble complex. So Ag plus aqueous plus 2 NH3 will give you Ag NH3 plus aqueous. Removal of silver ion is in the solution. Shifts equilibrium to the right, leading to further solubility of silver chloride. The solubility product of lead to chloride is 1.6 times 10 to the power negative 5 moles per decimeter cubed. Calculate the concentration of chloride ions in a saturated solution of lead. First, we write the equation. Lead chloride will ionize to form lead ions aqueous plus 2 chloride ions aqueous. Case P will be equal to concentration of lead 2 plus into concentration of chloride ions squared. Supposing X mole dissolve we will get X moles of lead ions plus 2X moles of quad ion. It implies that case P 1.6 times 10 to the power negative 5 will be equal to X into 2X squared. It implies that 4X cubed will be equal to 1.6 times 10 to the power negative 5. X is equal to cube root 1.6 times 10 to the power negative 5 over 4, which is equal to 0.016 moles per decimeters cubed. Therefore, the concentration of quad ion is equal to 2X, which is equal to 2 times 0.016, which is equal to 0.032 moles per decimeter cubed.